Hi guys, this is College Algebra, Math 1513 in Northern Oklahoma College. Section 4.2, we're going to talk about exponential functions. Okay, exponential functions, some of you guys probably already figured this out. It has the word exponent in it. That means we're dealing with exponents, and later on we're going to deal with unknown exponents and figure out how to solve equations that have unknown exponents. But for right now, all I want you to understand, in a nutshell, exponential growth is something that starts off growing very small, but then grows quicker and quicker until it's just skyrocketing at the end. Lots of people use the example putting money in a bank and leaving the interest in and just letting the interest compound and compound and compound. Well, at first you don't have very much money. You have very little money at first, but when you leave that interest in there and it grows, and then the interest gets interest and the interest gets interest, all of a sudden after 10 or 20 years you have a whole bunch of money, because that's called the miracle of compound interest. So let's mark this dollars in years. And let's say you put $1,000 in the bank. Well, at 0 years you have exactly $1,000. But as time goes by, you have a little more, a little more, a little more, and it starts growing and growing and growing because you left your interest in there. That's exponential growth. Okay, what if it goes the other way? What if we have let's say we have a car that we bought brand new for $10,000. Well, at year 0, when it's brand new right off the lot, it's worth $10,000. But as the years go by, your car becomes worth less and less and less and less until about when it's 10 years old, it's probably only worth maybe $1,000 or $2. And then as time goes by, it becomes worth less and less and less. It's hardly ever worth 0, but it gets worth less and less as time goes by. That's called exponential decay. The other one was exponential growth. When your bank account became worth more and more and more, exponential decay decreases and becomes worth less and less and less. Here's a homework problem you might see. They want you to evaluate the function f of x for 5 to the x, and these are the x's that they want you to put in. So I'm going to put in 3 for x and calculate f of 3. So I want to know what 5 to the 3rd power is. Well, that's just 5 times 5 times 5, which is 125. As an ordered pair, we'd say that when we put 3 into the function, we got 125 out. F of negative 2, we put that in for x, it's 5 to the negative 2. Now remember, negative exponents mean you're going to flip that number. Watch what happens. It equals 1 over 5 squared. Think about 5 to the negative 2 as being over 1. We can put any number over 1. And then you flip it upside down, and now the 5's on the bottom, and its exponent becomes positive. And we get 1 over 25. So if we put in negative 2 into the function, we get 1/25. And notice that's a small number. This is an example of exponential growth and exponential decay. That 3 for an exponent made the 5 get bigger, and if we put a 4 in there, it'll get even bigger. And if we put a 5 in, it'll get even bigger and bigger and bigger. So positive exponents are going to be an exponential growth formula. They're going to make the answer get bigger and bigger and bigger. The negative exponent produced a tiny number, 1/25. And if I put in a negative 3, it's going to get even smaller. And if I put in a negative 4, it's even going to get even smaller and smaller and smaller. That's an example of exponential decay. So negative exponents are related to exponential decay. Why don't you guys try this one? Pause the video and work it out. So I run negative 1 through the h function. It gives me 2/5 to the negative 1, which I flip upside down so that my exponent becomes a positive 1. And simplify, and I get 5 over 2. So negative 1 produces 5 over 2. And there's the next one. 2/5 raised to the 3rd is 2 cubed over 5 cubed. Exponents are positive, so we just leave them where they're at. Simplify to 8 over 125. Now sometimes it can get a little messy, but that's okay. So f of x equals 3 to the x, and we want to try negative 1.5. Now I could flip this over. See, it's 3 over 1. I could flip it over and make my exponent positive, but that doesn't really help me any because you can't really calculate in your head 3 to the 1.5. So we're going to have to grab our calculator. And we get about 0.19. What if I want to graph an exponential function like f of x equals 4 to the x? Well, the easiest way is just to put that in your graphing calculator and pull up a table. Or you can calculate it by hand. If I put in 0, well, I calculate 4 to the 0, that's going to give me a 1. So 0, 1 is my first pair. If I put in a 1, 4 to the 1 is 4. So 1, 4 is my second pair. And so on. But I'm going to use a graphing calculator to fill in the rest of the table. And notice that as I put in bigger positive x's, I get humongous y's. It's getting real big real fast. That's exponential growth. When I plugged in a few negative numbers, it starts getting smaller. And when I go to -2, it's really, really, really small. So let's see what that looks like on a graph. So I've marked 0, 1, and 1, 4, and 2, 16, and see how it's skyrocketing up. That's exponential growth. As we go to the left, -1 is about a quarter, 0.25, and then it gets smaller and smaller and smaller, and it gets closer and closer and closer to the x-axis, but it will never actually touch the x-axis. So exponential growth starts very, 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 very small, and then skyrockets. How about this one, 5/2 raised to the x? Why don't you guys try and graph this? Okay, let's look at our table. The first thing I want to point out is notice that when we put in a 0 for an exponent, we've been getting a 1 for our y. When you raise anything to the 0 power, it's going to be 1. That's a handy little fact to remember. Also, if you were calculating these by hand, you started off with 5/2 to the -1, which is 2/5 to the +1, which is just 2/5. If you guys are doing that by hand, and these are calculated in the same way, you just flip it over and straighten out the exponent. Notice, this is kind of interesting, how these kind of mirror each other. They're just flipped over. Okay, and this is roughly where our graph lies. Going through these points, exponential growth, getting closer and closer to the x-axis, but never actually touching it. Okay, a point we need to make right here is that 5/2 raised to the x, well, 5/2 is 2.5, and 2.5 is bigger than 1. 2.5 is bigger than 1, and what do we end up with? What kind of graph? Exponential growth. Now remember that on this next one that we try to graph. So on f of x equals 1/3 raised to the x, well, 1/3, that's a fraction. Fractions are less than 1. Hopefully you guys can guess what's getting ready to happen. So let's make the table and take a look at the graph. And here's our plot, our points for this one. Notice our 0, 1 was in the graph again. Exponential functions are always going to pass through 0, 1. And this is an exponential decay graph. So remember, if you're taking a number bigger than 1, you're talking about a graph that shows exponential growth. And if you're taking a number that's less than 1, a fraction, you're going to end up with a graph that shows exponential decay. What about translations? What if I give you f of x equals 7 to the x? We'll call that our parent graph. And what if I just perform all these translations on it? Which way does it slide? Well, hopefully you guys remember this from the other chapter about translations. Adding 4 to the end just raises the whole graph up 4. So it shifts the graph f of x up 4 steps. -4 out here on the end does the opposite effect. It shifts the graph of f of x down 4 steps. Now what about in the exponent itself? Now it's not what you think. You guys remember this? If I say 7 and I'm raising it to the x -4, well, that's the graph of 7 to the x shifted 4 steps. Now negative, you want to think it's going left, but it's actually shifting to the right. And adding 4 in the exponent shifts the graph of 7 to the x 4 steps to the left.